Okay? Good? You think you can handle the other two on your own? Yeah. All right, good. I'll let you. I wonder if these two are the same. If the order matters. Yeah, you wonder, or yeah, it does? What do you think? You think they're the same answer? Do you think the order is going to matter? We'll see. Clorox Theorem is going to answer that question right now. If f is defined on a disk, so remember these functions that we have right now are going from two-dimensional space into one-dimensional space, right? We're taking our input lives in R2. The output lives on a number line, right? I've been trying to stress this for a while. We can visualize this as a surface, can't we? This is saying that if your function is defined on a disk, so defined means talking about domain. If you look at a little disk in here, okay? We'll call that disk D. And there's a point in here that lives in here called x naught, y naught. So you look up on this disk, up where the surface is, right, coming out at us. We turn it over and then we're like that, right? So that surface, as long as there is a surface above this disk, and f of xy and f of yx. So that means the partials in both directions, as long as those partials are both continuous, meaning that they're not going to like have asymptotes or become undefined, as long as they stay well behaved on that disk, then you're guaranteed that the partials are the same both directions, both orders. If you do the partial with respect to x, then y, it should be equal to the partial with respect to y, then x. So the condition is that your function is defined on this disk and that the second partial derivatives are both continuous. So without us actually doing it, let's look back at that problem I just asked about, this one. Should, according to that theorem, should this be equal to this? Yes or no? Why or why not? Explain, please. You saying yes? Yes. Why? Because you did it and checks? Good.
There's no natural laws or divided by.
Yeah, there's nothing bad. This is a polynomial function, right? Last class we said that all polynomial functions of two variables are continuous everywhere, right? So the derivative, no, I don't care how you take a derivative of this with respect to x or y, it doesn't matter. It's still going to be a polynomial function, isn't it? And that's going to be continuous. And if you do a derivative again, it's still going to be a polynomial function, and that's going to be continuous. And what you need for this theorem to work is that the second partials are both continuous, and they will be. So you're guaranteed that these are going to be the same, all right? Or you can just check it. Now, there's nothing stopping us from doing just second partial derivatives. You can have third partial, just like in Cal 1, you can have first derivative, second derivative, third, fourth, fifth, sixth. But in Cal 1, really, just the first and second derivatives were the ones that really mattered, right? Those are the ones that really helped us. But there's nothing stopping us from doing a higher order derivative. So let's see if we can make sense out of what this one is right here. F x, y, y, x. So I'm going to take the partial with respect to x first, then y, then x. Let's see what we get. So first, start with the partial with respect to x. So what would the partial with respect to x of that be? We've already done this problem, right? 2x minus 30 x squared y squared. Isn't that what we got? Now the partial of that with respect to y. which is 0, and then negative 60 x squared y. That's also the one we just did, isn't it? Now let's do the partial with respect to y again. What's partial with respect to y of this?
60x squared.
Negative 60x squared. And then finally, what's the partial with respect to x of that? So what's the partial? What is it? Negative 120x. Part B asks you to do a different variation. Partial with respect to y, then x, then x. If you keep doing this, aren't you eventually going to get down to 0? Right? Aren't you? Will that always happen, you think, with a function of two variables? If you just keep taking partials over and over, do you think it's eventually going to become 0? Polynomial functions, yes. But if it's something other than a polynomial function, not necessarily. Yeah, cosine sine could turn into a mess. And that's also something you saw in Cal 1. Sometimes derivatives get nicer, sometimes they don't. Now here's an application of this. Laplace equations, differential equations. This is, you take a course in differential equations, you'll talk about Laplace. Maybe. Do you talk about Laplace a little bit? Yeah. So if you have, first of all, what is a differential equation? A differential equation is any equation that involves the derivatives of functions. So you have some function, you have an equation that has derivatives in it, that's a differential equation. Now there's a whole lot of different categories of differential equations. This right here is what we call a Laplace equation. And it's starting out by assuming that you have some function of two variables. So we've been using f of xy, but there's nothing stopping us from calling it u of xy. Equations have solutions, don't they? They should. I mean, they don't always, but the whole idea of having equations is to try and find a solution. The solution to a differential equation is actually a function that satisfies that equation. Instead of a solution like x squared minus 4 equals 0. Here our answers are numbers, right? An equation like this, the answer is actually a function or a family of functions that satisfy that equation. And so what we're trying to do here is come up with some way of determining if functions will satisfy that or not. All of them which do, okay, functions which satisfy that equation are known to satisfy the Laplace equation. That's all they are. It's just a whole category. But you have to check them, all right? Here we go. Determine if this function is a solution to the Laplace equation. Is that a solution? So what you're going to check is to see if that equation that we just had a second ago is true. Now, let's point out some things about this. Here's that different notation, isn't it? The offset 2's. This means you're going to take the partial derivative with respect to x twice. You're going to get that answer. You're going to add it to the partial derivative of the function with respect to y twice. If those add up to be 0, then this is then the function you're looking at is a solution to the Laplace equation. So the question was, is this? So I'm going to need to know what is the partial of u, second partial of u with respect to x, right? What is that? And I'm also going to need to know what the second partial of u with respect to y is. Now, as much as I love that notation, what this really means is uxx and uyy, okay, which is a little cleaner writing, right? So what is uxx? Let's just figure it out right here. This is all just what I'm thinking. What's u sub x? Three x squared plus 3y squared. You'll agree? Partial again with respect to x. 6x. Okay, now let's look at the partial with respect to y. Partial with respect to y is 6xy. And then the partial with respect to y again is 6x, right? So now the question, does this satisfy the Laplace equation? Yes or no? Does uxx plus uyy equal 0? Does 6x plus 6x equal 0? No. Well, it does if what? If x is 0. But if x is 0, then what's the function? The 0 function, and that's boring, right? That's the trivial solution. It doesn't make any sense for us to think about that. So what we're looking for is a family of functions that satisfy this. This definitely does not live in that family. So what do all the solutions to Laplace equations look like? No? I'm not going to put you on the spot. No. They all have the same look to them, no? Okay, we won't. Hey, remember implicit differentiation? Things like in Cal 1 where you had like y equals sine of xy, and you were trying to find what the derivative of y was, what y prime was, and you couldn't solve for y, so you just had to do this implicit differentiation. Same story here. We can do implicit differentiation, but it's partial implicit differentiation. Because look at our equation. How many variables does it have? 3. Right? You cannot solve for z here. Look, if you look at this, you cannot get z isolated. Well, you could, but then the z would be on the other side. So there's really no way of getting z isolated. Do you all see that? So there's no way you can write z as a function of x and y. But we know that all these variables are connected together, don't we? In fact, if we have an equation that involves 3 variables, what does that draw? Should be a surface, right? Could be a sphere, could be an ellipsoid, could be a hyperboloid, or all these different things, cones, right? Now this one actually doesn't fall into any of those categories, but it's a surface. How is a surface, a general surface, different than this sort of thing? This is very fundamental. Let's see if you can connect this. Like, what is the difference between that and something like, if I graph these, what's the fundamental difference? Are they both surfaces? Yes. This one, though, is special because you could solve for z, right? It doesn't have to be flat, though. This could be wavy around like a blanket in the room, just kind of, just wave a blanket and then freeze it, and then whatever it is, that's our surface, right? So this is like some wavy surface sitting here in 3-dimensional space, right? Here's the ground, and for every point we plug in, we pop up and we hit the surface, right? Think of like a vertical line test. If I were to sit here and take something and punch through this surface, I'm going to go down, or maybe I should start at the domain and go up. I'm going to hit that surface, right, in one point, and I'm never going to hit it anywhere else again, am I? Over here, though, what would happen? That's a ball, right? Surface. If I were to take some point and go up, I would punch out, right? I'd punch out of the ball. But if I went down, I'd punch out of the ball too. Do y'all see that kind of fails the vertical line test? Like a version of the vertical line test? This is not a function of x and y. This is. See the difference? But, yes or no?
Yes.
Okay, but does it make sense to you, there's a red marker, does it make sense to you that we should still be able to stand on that point and then look down parallel to the x-axis and find some tangent line slope there? And does it make sense that we should do it the other way too, pointing in the direction of the y? We should be able to do that still, shouldn't we? Even though there's another point on the other side. We should be down there and be able to point, parallel to the x and y axes and still get two different answers. Yeah? Our way around this trouble is implicit differentiation. It allows us to still pick these up, even though this is not a function of x and y anymore. All right. I'm wondering if y'all are really connecting this. I'm not sure. I gotta take you back, because whenever I get the feeling like y'all are just like nodding to agree with me, I feel like I have to go back. Look, y equals f of x cal 1. Can you find the slope of the tangent line? If it's a function of x, can we find the slope of the tangent line? Yes. Okay, if it can't be looked at as a function of x, like here, it looks like a circle. It still is reasonable for us to ask about the slope of tangent line here and tangent line here, isn't it? The way we did that is we did implicit differentiation on this. That's how we were able to find it. Can anyone tell me what the derivative of this is implicitly with respect to x? So what's the derivative of y with respect to x here? What would we do? Derivative of this is 2x. Very careful here. What's the derivative of y squared? 2y. Y prime or dy dx, depending on your instructor. I'm going to say y prime. And then equals derivative of 1, which is 0. And then you move things around. 2y, y prime equals negative 2x. You divide through by 2y. This looking familiar? And you get y prime is equal to, what is that? Negative x over y. Right? That's what you would get. So what this said is that if I want to know the slope of the tangent line on this circle, you're going to have to tell me what? Not only the x coordinate, but the y coordinate. And so if you tell me the x and y coordinate, like someone tell me the x and y coordinate at that point. What's the x and y coordinate at that point if this is the unit circle? What's that point right there? Unit circle. Root 2 over 2, root 2 over 2, right? Yes? Plug those in to here, and what do you get? Root 2 over 2, root 2 over 2. What do you get? Negative 1. That's the slope of that line, right? Now, what if you plug in this point instead? What's the difference in their coordinates? Root 2 over 2, but now negative root 2 over 2. And if you plug that into here, now you get positive 1 in near this line. You see that? So that's what implicit differentiation allowed us to do. It allowed us to find slopes of tangent lines on things that were not functions. That's exactly what this is doing. It's saying, hey, look, this is not a function of x and y anymore. It might be an ellipsoid. We can still find slopes of tangents on there as long as we can take the derivative, and we'll do it implicitly. I hope that helped. All right, so we're going to do it. We're going to start with this one. Partial of z with respect to x. So what this means, z is the function itself, right? We are assuming that z here depends on x and y. We just can't solve for z. The x tells us that we're going to treat x like a variable, independent variable, and we're going to let y be constant in the problem, right? That's what this means. So what I'd like for us to do this, right? That's what I'm about to do right here. I'm going to look at this equation. I'm going to take the derivative on both sides, partial derivative with respect to x. So what would the derivative of x cubed be with respect to x? 3x squared, just like we think, right? What is the derivative of y cubed with respect to x if y is a constant? 0? Well, 0. Plus, now, what is the derivative of z cubed if y is a constant and x is a variable, and we're saying that z depends on x? 3z squared times z prime, which now we're going to write, instead of z prime, we can't get away from it now. Partial of z with respect to x. See, this is the z prime. But we need to be specific now because we have more than just two variables now. Or we have, x and y. It was kind of easy to just write y prime because there was no confusion. Now we need to be a little more specific. Any questions on that? That's derivative of y cubed. Z cubed, sorry. What's the derivative of this in here? Oh, shit.
Six.
What's a constant? Let's see what's a constant first. Y is a constant. 6 is y and the 6, right? So I'm just gonna bring those out. 6y, right? That's a constant. I'm just gonna say forget that. It's just coming along for the ride. So what's left here is x times z. What's the derivative of x times z? Product rule. You have to use a product rule because they're both variables, right? X is a variable and z depends on x. So do a product rule right here between x and z. What's the derivative of x? 1 times z plus, what's the derivative of z? Partial z with respect to x times x equals, we're done, right? We're done with this? Equals what? Derivative of 1, which is 0, right? That might be off the camera, so I'm going to put my 0 on this side. All right, let me try and clean it up. 0 equals 3x squared. This is gone. Plus 3z squared partial z with respect to x. I'll distribute through here. Plus 6yz plus 6xy partial z with respect to x. Did I distribute properly? Everyone agree with that? Now, what did we do when I was showing you that circle one just a second ago and we did the whole partial thing? Didn't we isolate the y prime? We got it by itself on one side of the equation? That's what I'm doing now. When I isolate the partial z with respect to x, which is what I was trying to find, right? Let's get that by itself. So why don't we move everything else that doesn't have that to the other side of the equation? So let's move this, and let's move this to the other side. So we have negative 3x squared, minus 6yz equals 3z squared partial z with respect to x plus 6xy partial z with respect to x. Why did I do that? Why did I move the stuff that didn't have the partials over? Why did I do that? So I could factor out, right? I'm going to factor out a partial z with respect to x out of both of those. So we have left side is negative 3x squared minus 6yz equals, when I factor this out, I guess I'll put it in the front, doesn't matter. Partial z with respect to x, and then I have 3z squared plus 6xy. And finally, divide both sides by what's in parentheses here. So negative 3x squared minus 6yz over 3z squared plus 6xy equals partial z with respect to x. Good? So remember I just gave you the example of the circle in two-dimensional space, and I said, hey, look, if we want to know the slope of tangent line, we actually have to know the x and the y coordinate because those are going to give us two different values, right? What we're saying is if you're sitting here on this surface and you're out there and you're trying to figure out the slope of the tangent line, here we're going to be running parallel to the x-axis because that's what that means. Then this surface could actually fold over and there could be another part below. So I'm going to need to know a little bit about where you are. And is that obvious from this? What are you going to need to know to have this partial? The x, the y, and the z. You're going to need to know exactly where you are in order for me to be able to spit out the answer. Understand? All right, I will leave the other one for you as an exercise. Not for right now, but everyone understand that's different, right? That's a different implicit differentiation. And that is the homework assignment that goes with that. And that's what I just finished today. I just posted the video. It's not a real tough assignment. Well, I keep on saying that. It's easy. No. It's not the first time you've seen integration type problems, you know. When you're trying to learn like integration by parts and all that, it takes like some beating to death before you get it. This is more like once you see it, it clicks. It's pretty straightforward. Let me see where we are here on our calendar. I haven't looked at this in a while. What's today? 17th. That's all we're supposed to cover. So. This is going to be a very short section. When we finish this, I'm not going to push forward anymore. I think that'll be probably enough. And I'll let you all go if we end a little early today. Or maybe we can stay, hang around, do quiz or something, whatever. Tangent planes. So we talked about this last class a little bit. Tangent planes. What do you need to define a plane? Point and normal vector, right? Point and normal vector. In fact, we've seen that the equation of a plane do you remember this equation of a plane that I gave you all way back in the day? That the ABC out of that was the normal vector, right? Came from the normal vector. The normal vector of the plane, or you know, I should remind you this way. Remember this one. Ax minus x naught plus b times y minus y naught plus c times z minus z naught equals 0. Remember that equation? There the normal vector was ABC. Now look at what I have here. A tangent plane to a surface. So we have some surface living there in three-dimensional space. Right? If we've got this surface and it has continuous partial derivatives. I misspelled continuous. It has continuous partial derivatives. Then the equation of the plane, which is tangent to the surface at a given point, is given by this right here. Does that look complicated? What does that look like to you? Does that look complicated? This right here, well, look, they have to give you a point, x naught, y naught, right? That's given. You have to be standing on a point on the surface. Maybe it's the point 2, 1, like we were at 2, 1 at the very beginning of class. I came out 2, I went over 1, right? So let's go back to that. If I go out 2 and I go over 1, we said that pointed in this direction, it was 6. This direction was 23, right? Remember that? What this is saying is that, well, if I'm pointing out 6 this way and 23 this way, what is the equation of the plane that is tangent to that surface at that point? Well, here's the equation of the plane. It looks very similar to what I just had up here. This is the A, this is the B, and C is what? Always going to be -1. What is C? It's the z component, right, of the vector, the normal vector. -1 is pointed straight down, isn't it? So that's how these partial derivatives come into play in this equation. You're just going to have to figure out what the partial derivative of the function is with respect to x. You're going to plug in the point 2, 1. That's going to be a number, isn't it? That number is the first number in the direction vector for that normal. And then the partial with respect to y, plugged in the 2, 1, that's going to give you this part. And then the good thing is c is always -1. So that's what I'm saying here. The normal vector is just this. Let's see if we can do an example. When I talk, let's talk before we talk about tangent planes. Let's just clarify from Cal 1 tangent lines. The idea of a tangent line from a circle, right? When you first learn about tangent lines, how would you describe to someone what a tangent line is off a circle? How could you verbally explain to someone what a tangent line is? It touches it at one point. It is a line that touches the circle at just one point, right? So if I draw 2 points, obviously there's a line that goes through those. That's not the tangent line. If I move this point closer, then there it is, right? But I'm looking for the line that only goes through at one point, right? Which would be that. There's only one line that does that, right? That's the tangent line. Now, you could also say that that tangent line is perpendicular to the radius, isn't it? Any tangent line that you draw will be perpendicular to the radius. Now, the reason I'm asking you to think of this is because back now when you looked at Cal 1, you had a function that went like this. And we were asked to, let's say, find the slope of the tangent line here, or find the tangent line there. Can you still use the same definition that it only touches the function in one place? I mean, do we all agree the tangent line looks like it should be about like right there? Now here, it's just going to touch at one place. But back here, doesn't it hit? So you can't use that same definition like a tangent line at a point is a line that touches the function at just one point. You could say that in some little neighborhood, right, it only touches at one point. But you can't say on the entire domain of the function it only hits at one point. So when we talk about tangent lines, we're just looking locally, aren't we? Yes? We have the same idea here when we're trying to find the equation of a plane which is tangent to a surface. We're saying just at that point, locally, it touches the surface at one point. Maybe somewhere else it might hit, but locally it's going to just touch. Let me extend everything now, this picture and this picture, into 3D. Here, if I ask you to tell me about a tangent plane, just imagine putting a sheet of paper or a flat piece of cardboard on top of a basketball, right? That plane would be touching right there at the North Pole, right? And that would be tangent to the ball because it's only going to be touching the ball right there at the North Pole, yes? But if we look at the surface in general, then see, this is where it becomes very difficult for me to draw.